So this week I will explain how to solve convex optimization problem with gradient descent approach. Okay, so let's consider a very simple convex optimization problem where there is no constraint on input x. And the function form, objective function form is very simple, x minus 2 square. So can you solve this problem? I think this is very easy and you can very easily find the solution. X equal to 2, the objective function is minimized with value 0. So why this problem is so easy? Because we know the exact equation function, right? So from the equation we can easily say x equal to 2 can minimize the objective function. Even if we don't know the exact function form and we can only access to the gradient value at each point, still this is very easy task because the gradient is very simple. At each point the gradient is just 2 times x minus 2, and from this we can easily find the critical point x equal to 2. When x is equal to 2, then the gradient is equal to 0, so which means x equal to 2 is a critical point. And we know that in convex optimization problem, all the critical point is the optimal, global optimal point. So essentially from the first derivative function, the gradient value, we can easily find the solution x equal to 2. So gradient descent algorithm utilizes the gradient value. When the objective function is just a quadratic function, we can very easily find the solution as in the previous slide. But even if the function is not quadratic function with the gradient value and gradient descent algorithm, we can easily find the solution. So this week, I will introduce how to solve the convex optimization problem using gradient descent approach, and how many number of computation we need to find the optimal solution using gradient descent approach. So gradient descent approach is very simple. At every time we have point xt, we start from xt, and we compute the gradient value, gradient of f at point xt, and we move the point xt to the opposite direction of gradient, because gradient essentially is the direction we increase the objective function value. So we have to move opposite direction of gradient. When we update xt plus 1, the point at iteration t plus 1 is basically just equal to xt minus gamma times gradient of fxt. So we move opposite direction of gradient value with gamma step size. Okay, so when gamma is big, gamma is large, we move a lot. When gamma is small, we move very little bit. And gamma could be a function of t, so we can control gamma t like 1 over square root of t, 1 over t, and so on. So we usually say gamma is learning rate. So gamma is referred to as learning rate or step size. Gamma is learning rate or step size. Okay. And to analyze the performance or the efficiency of gradient descent algorithm, we usually analyze the convergence rate. So we want to find the t that satisfy fxt minus fx star less than or equal to epsilon. So we want to find out how many iteration we need to be epsilon close to the solution. Okay. Right. So basically, we will find the answer for this question. So when we have objective function And we want to analyze fxt minus fx star for the gradient descent algorithm with some constant step size like 1/2 or some other step size gamma or time dependent step size gamma t. Okay, right. And let's find out solution for this first, for this very simple task. Fx is equal to x minus 2 square. Okay, for instance, x0 is equal to 10, and xt plus 1, we update xt plus 1 using gradient descent, xt minus step size 2 times xt minus 2, because 2 times xt minus 2 is the gradient value. And let's assume gamma is equal to 1/2. Then this value is equal to just 2. Always. Which means with one single iteration, even x1 is equal to 2, x2 equal to 2, and we know that 2 is the solution. So with one single iteration, we can find the solution. So it looks like the gradient descent is very efficient approach. We can immediately find the solution with gradient. But this is not all the case. We usually cannot convert to the solution with one single iteration, but we need a lot of iterations, and which depend on the function shape. If the function is very beautifully looks like this quadratic function, maybe we can go to epsilon optimality with one single update or two updates. With very few updates, we can convert to epsilon distance. But if the function is not looks like quadratic or some other shape, maybe we need a lot of iterations. So we will discuss which term of your objective function change the convergence speed. Okay.